This video presents Matador, automated system-on-chip Tsetlin machine design generation for edge applications. I'm Tausif Rahman, and this work comes from the Microsystems group at Newcastle University, and this is the presentation we are submitting for Date Conference 2024. I'd like to start by discussing some of the motivations behind the Matador tool. Starting from the top red box, we see that AI-enabled sensors allow for machine learning applications to be performed at edge nodes. Now this means that there are clear advantages in terms of reduced network bandwidth reliance from data transfer, increased security and privacy of the data, and the edge nodes are typically low power devices, which leads to far better energy consumption compared to cloud-based solutions. However, this also creates deployment challenges, and the core of which we summarize by saying, how can we achieve satisfactory speed and accuracy of the ML model when the compute and memory resources are limited? For achieving suitable speed, one of the most widely used methods is through hardware acceleration, and recently this has become a more attractive option at the edge with the advent of low-power embedded FPGAs. Now if we look at the pink box at the bottom, we can briefly overview the main ideas for embedded FPGA acceleration that are being used by current solutions. The roofline diagram is a good way of comparing computational intensity given in gigaops on the y-axis with arithmetic intensity which is given on the x-axis. The arithmetic intensity here is defined as the number of operations that are performed for each byte that is read or written from off-chip memory. For a given hardware platform, where the line is sloped indicates where the bottleneck is limited by the data bandwidth, but where the line is horizontal indicates where the bottleneck is the computational intensity. This particular graph is for a convolutional neural network, or CNN, and these models are typically used for inference applications at the edge. Notice that where the bit precision of the weights is reduced, the computational peak, i.e. the horizontal section of the graph, starts to happen at a higher point, and we really benefit from this when the bit precision is reduced to a single bit. Current works try to find a good trade-off between the low bit precision and the model accuracy, and this is not so easy with neural network-based models due to the large number of hyperparameters and large design spaces that are possible, and it makes automating edge deployment for these models quite difficult. One of the core differences between Matador and works that are automating the deployment of conventional neural networks is that Matador is built on an ML algorithm that is intrinsically bitwise and doesn't suffer the same precision losses. Secondly, the architecture of this model is quite simple and it leads to very small design search spaces, and it makes the approach very easy to automate. The model in question is called the Tsetlin Machine, abbreviated to TM. And in the upcoming slides, we will examine how the TM works and what the advantages are of this logic-based learning system. The TM can be described as an ML algorithm that creates logic propositions to determine classifications. The TM also has some key advantages that make it suitable for edge deployment, including explainability, because it is logic-based, it has intrinsic explainability, intrinsic sparsity once the model is trained, fast inference from bitwise compute, and low complexity hardware. Let us quickly look at the fundamental components of the TM as it trains on an XOR learning problem. Let us start by looking at the structure of the TM. The TM for XOR has two classes, y equals 0 and y equals 1. And for each of these classes, we've chosen to have two clauses. These are where the logic propositions will be formed. Now, the inputs to the TM are the XOR inputs, but they are then split into the X and X bar components called Boolean literals. Each clause contains all of the literals which are represented with a Tsetlin automata, which can oscillate between include and exclude states, which we see in the red and the blue. Let's start the demo. At the start of the training process, each TA is initialized somewhere close to the middle state. Now the inputs are loaded. The inputs are then split into their Boolean literals. Now, each literal will be processed by every clause. To generate this clause output, we extract the value of each Tsetlin automata, where an include corresponds to a 1 and an exclude corresponds to a 0, and from this we can perform this NOT, or, an AND-based logic compute for every clause in every class. Once clause outputs are generated, we multiply them by 1 or minus 1 depending on the clause polarity. For every class, half the clauses will have a positive polarity times by 1, and half the clauses will have negative polarity times by -1. Next, all the clause votes are summed for each class, and we take the argmax of the sums to provide the classification. During the training, based on these outcomes, reward and penalty signals will then be applied to these automata. Feel free to watch this section again if there's any confusions. Now let's look at how these automata behave during a full training process. The y-axis here represents the number of states in each automata, while the x-axis represents the indexes of each TA in the full TM. Let's examine what happens when the learning process starts. Notice that the majority of automata go into exclude states, with a very small number choosing includes. This results in a very sparse model after the training is completed. Now that we've seen the characteristics of the TM, let's explore how Matador uses these to generate automated edge deployment TMs for inference applications. The main idea behind the Matador approach is to take the learned logic expressions in each of the clauses and create custom compute units from them for every class. We then integrate this with the rest of the inference process for the TM that we saw earlier. This allows us to auto-generate the accelerator RTL, which we then integrate into a system-level RTL. The rest of the Matador process is about automating the synthesis, implementation, and testing of the generated hardware. Altogether, we find that Matador enables us to create very fast and resource-frugal inference accelerators based on Tsetlin machines. Compared to its closest state-of-the-art from Xilinx, we find that there are significant performance gains from Matador. Now let's have a closer look at the Matador architecture. We start by examining how the inputs are fed into the Matador accelerator. Notice how the binary vector, the binary features that are the inputs to the TM, are now split into packets. These packets are used to create a data stream. The width of the packet is dependent on the bandwidth between the processor and the accelerator. Now let's see how the packets are used for computing by the accelerator. The compute space may be visualized through this matrix below, where the x-axis indicates the feature index and the y-axis indicates the clause index. The intersection between the two is highlighted with these pink blocks. Within this intersection, if the feature or its complement is included, the operation within the intersection is simply an AND product with the rest of the clause expression. As we saw earlier, the bandwidth limitations mean that not all of the features will be seen at once, and therefore W features will enter the accelerator each clock cycle, where W is the bandwidth. This means for each W section, we perform the custom compute indicated by the pink intersection point and pass on the partial result until we get to the end. When this is passed to the synthesis engine, we get some optimization advantages when a feature is shared across multiple clause indexes. Now let's have a look at the big picture of the accelerator design. The W-separated sections we saw earlier are now represented as HCBs, or hard-coded clause blocks. And we can see from the expanded view that each of these HCBs is actually created through custom AND products. Data is sent through an AXI stream interface indicated by the grey blocks, and routing the appropriate packet to the appropriate HCB is done through the HCB controller. The inference process therefore becomes computing the chain of the HCB blocks followed by the class sum, the argmax, and sending the result back through the AXI master. Now let's have a look at how the accelerator is integrated into a larger SoC and how this whole process can be automated. This figure represents the design and refinement cycle of the Matador accelerator. Starting from the top left, we see that the main idea is that the user uses a GUI to guide them through the process of training a Tsetlin machine, generating RTL from the extracted clauses, creating the accelerator and integrating it into a wider SoC and testing. On the top right, we see the output clauses after the training process. These clause expressions are then used to generate the hard-coded blocks we described earlier. Then standard synthesis and implementation tools are used to deploy onto the FPGA, where a corresponding test is generated to test the metrics that the user is interested in. This figure shows the design and debug methodology proposed by Matador. The user is offered various freedoms in terms of parameter choice when it comes to model configuration for the training, adder stages that are used for the class sum, or the frequency at which the design will run. They may also choose to validate their design through auto-generated test benches and integrate their design with a logic analyzer so that they can test this after the hardware has been built. Now let's look at the experimental results from different Matador accelerators. To evaluate the results, the core metrics that we are looking for are resource usage, which we see at the top in the dark grey, the test accuracy from the model, the total power and dynamic power, which we extract from Vivado's power reports, the latency for a single inference, and the throughput that we get from the accelerator. We choose to compare Matador against Finn, a automated BNN generation and deployment flow from Xilinx. We do this because this is the closest comparable work to Matador, and also it offers the fastest execution times on the MNIST dataset that we've seen to date. The top two pink rows represent the Finn implementations from Xilinx that get the fastest execution times reported to date. These results are hardware specific and specifically for the MNIST dataset. For a closer apple-to-apple comparison, we deploy Finn on the same board as Matador for a variety of different datasets, including audio ones called keyword spotting, which we see through the keyword spotting 6 with 6 keywords, and a subset of CFAR, which we use to determine whether Matador is successful at image classification. To summarize these results, we may say that Matador offers better resource efficiency and also is generally faster for both audio and image classifications. These advantages can probably be characterized through three things. Firstly, the simplicity of the inference algorithm, which we saw earlier, the intrinsic sparsity, which is then seen at the clause level, where the length of the AND products is limited, and thirdly, by the synthesis optimizations, and this is seen through the logic sharing of AND products which may be shared across multiple clauses. To quantify the extent at which the AND products are shared between clauses, we run the synthesis with and without the shared optimization, and we examine the LUT and slice register count, and this is seen by the bar chart at the bottom. We see that across all of the HCBs, there is a reduction in the number of elements that are being used when the synthesis optimization is enabled. This may happen because of logic sharing within the HCBs and intra-HCB. Now that we've seen the core components of Matador and how it performs against the state-of-the-art, we can make some closing remarks for this presentation. From the accelerator design, we see that the accelerators are fast and simple, and the simplicity comes from the simplicity of the TM algorithm, and the speed comes from the bitwise operations that are being used, and both of these are intrinsic to the algorithm itself. The direct result of this is that the accelerator designs become very easy to integrate into SoCs and to automate. One of the core benefits is the resource frugality, and that comes from two core concepts. Firstly, there is the sparse learning, and this is seen through the length of the AND products within the clause expressions. Typically, we see that the clause expressions themselves are relatively small. And secondly, there is the advantages we get from synthesis tools through shared expressions. The current implementation of Matador focuses on the vanilla TM model. This is the standard TM, but now there are many others, and future works will investigate the approaches of automating these as well. Matador is offered as an open source tool, and we've provided the GitHub link here. Thank you for listening, and hopefully this has been an interesting introduction to Tsetlin machines and how Tsetlin machine accelerators can be created through the Matador tool. If there are further questions, feel free to get my contact details from the GitHub link.